Yeah, so today I'll be talking about some of the tools and frameworks that we use here at ALCF for scaling deep learning applications and use for distributed training. So as I was saying a bit before, but people might have missed it, all of the information contained in these slides is also available in on the Computational Performance Workshop GitHub repo. So it's just arranged a bit differently, things like that, but it's all the same content between the two. So I'll get started by talking about some of the different types of distributed training, specifically why it's advantageous and how it, some of the different forms it takes. The main point though being that why are we interested in scaling deep learning applications and distributed training in general? And the main reason, so I guess there are two main reasons, right? So the first case being that if you have models that don't fit entirely on a single device, or you have data that needs to be split due to memory constraints, then obviously it's a necessity and you have to get creative with how you split things up. The other reason being that splitting data across workers has the effect of effectively increasing the batch size, which in turn has the effect of generally smoothing the loss landscape. So it makes the general training procedure a bit smoother and smooths out some of the possibly sharp peaks in your loss landscape. It also can help to improve gradient estimators. So gives you, it's possible to give you a more reliable estimate of the gradient, when approximating gradients. It generally requires less iterations for the same number of epochs. So it's possible that you may need to train for more epochs if you don't implement some other compensating change. So for example, boosting the learning rate is a common approach, which just scales the initial learning rate by the total number of workers. And so there are a lot of different reasons to train on multiple GPUs or use distributed training. And there have been a lot of advances in this area in recent years. So there's a good reference here on this archive paper that looks at large batch training of convolutional networks and does a good job of describing all of the details specifically. We can look at it even just, in terms of looking at total training times for specific models in recent years. So this is pulled from this paper on the previous slide, but we can see that between 2016 and 2019, just by increasing the effective batch size by scaling across more GPUs and more workers, they've different deep learning libraries as well, but the main point being that they are able to cut the total training time down from 29 hours in 2016 to 1.2 minutes in 2019, simply by increasing the general batch size, which can be done by increasing the total number of workers. So for example, you can see here in the beginning, they had 8 P100s. And so, there's also changes in architecture and things like that, but just simply by, increasing the batch size, you can have this dramatic reduction in overall training time, and generally allows for faster progress, things like that. So there's a lot of references and resources. I kind of aggregated some of them here, but they're also all available on the GitHub repo, listed maybe a bit more sequentially, but there's a lot of good references directly from PyTorch and Horovod, which are two of the big libraries for distributed training. And so all of their internal documentation and examples and things like that are a good place to start. To give some context into the general development trajectory of deep learning applications, this is pulled directly from one of the PyTorch documentation pages. And so this kind of outlines how applications generally proceed. So you have some new idea that you want to try a new model architecture, and you experiment with different prototypes on single device, which just kind of allows for rapid prototyping and quickly trying new experiments. But that's obviously not efficient when you want to scale up or run, production scale runs. And the next kind of maybe naive approach would then be to use a single machine multi-GPU, which takes advantage of PyTorch's built-in data parallel library. But again, this is, even in coming straight from PyTorch's documentation, this is not recommended, and they generally recommend using their internal distributed data parallel library, which is also known as DDP. So the whole reason why they have this separate library in the first place and make mention of it only to say that it's not the recommended method doesn't make a whole lot of sense, but this is just coming straight from their documentation. And so the points we'll be focusing on today are using single machine multi-GPU distributed data parallel training. And that can be done either, one of their one of their built-in implementations. So they have tools internally for launching and dealing with communication and initialization between different workers. And they also provide this separate launching script that kind of takes care of all of that for you, which is convenient as well. They also have on this page as well an additional point here that emphasizes using their built-in Elastic distributed library, which I haven't used personally and don't have any experience with, but seems to be a bit newer and handles things like fault tolerance and automatic continuation and dynamic allocation of resources and things like that. So I think this is kind of an up and coming library that probably has some kinks in it, but may be useful for certain cases where you have non-standard resource requirements or things like that. Next, I'll talk a bit about some of the different type of distributed training approaches and what are the differences between them. And the two main types being what are called model and data parallelism. First, I'll talk a bit about model parallelism. And this is the case where you have a network model which is too large to fit on a single device. And so what you do in this case is break up your network and assign disjoint subsets of the network to different devices. In this case, you have communication associated with completing different parts of the model, right? So you have to worry about getting data from different workers in order to proceed in the forward pass, for example. And so this is an approach to, one method of dealing with the problem when you have a model that's too large to fit on a single device. And so it can be done. It's typically more complicated to implement than normal data parallel training, which is the more common approach. But it's suitable as I said before, it's suitable when the model is too large to fit on a single device. The actual process of partitioning the model onto different devices and doing that in a clear and easy to understand fashion is not always easy. And you always run the risk of introducing load imbalancing issues, which could then impact the scaling efficiency. And so you really do kind of have to be careful how things are set up in this case. And there are a lot of nuances and things that can possibly make your life difficult when trying to use model parallelism. The documentation on the Hugging Face Transformers website is a good reference, and they have a lot of general documentation and examples illustrating how to distribute tensors on different devices and generally just best practices for things like that. This is probably easiest seen by looking at an example. So here's kind of just the diagram illustrating how model parallel training could work. So in this case, you have multiple different workers here illustrated as different GPUs. And you can see that the model is kind of distributed across these different GPUs. So GPU 1, for example, has this node of the model. GPU 2 might have, for example, these two. And setting things up this way, you're able to put different parts of the model on different workers and feed the batch of data in as you would normally. But one kind of problem with this approach is that in order to complete the full forward pass at different points of that computation, you need to pull in the values of different weights from different workers and deal with the overhead and the introduction of additional overhead from that communication and things like that. So this is, has value and is useful for cases where, again, you can't fit, just due to size constraints, you can't fit the entire model on a single worker. And so there are ways of dealing with that in that case. Next, I'll talk a bit about data parallelism, which is typically easier and simpler to implement and is generally probably a bit more common just due to the fact that it's easier to set up and more generally applicable. So there are a lot of existing frameworks that kind of help you get set up for this approach. For example, Horovod is one pretty well-known library. Microsoft DeepSpeed, which is relatively new, but also has been gaining popularity recently. PyTorch's built-in DDP, which is distributed data parallel, their library for data parallel training. And so there are kind of a lot of different libraries that take slightly different approaches and have different requirements for getting them set up. But there's a lot of different options, and they're typically relatively simple to get up and running, requiring minor modifications to the existing code bases. So this topic has been covered previously at different workshops here at ALCF. There's a link here to a previous recording from one of our presentations on data parallel training on YouTube. So in this so a bit more detail now about this data parallel approach. So in this case, all of the workers own an identical replica of the model. So each worker has the complete copy of the network, and the global data that you're going to process gets split into multiple mini batches and processed by different workers. And so in doing this, each model on the different devices sees a different set of data. And after each forward pass of the network, basically each individual worker computes its local loss and gradients with respect to the data that it has kind of locally. And then there's kind of a global all reduce operation that syncs the gradients between all the workers, which will then allow them to all backpropagate and update their weights as needed. So there's a lot of documentation and resources online that detail how this happens. The link to this Horovod documentation is particularly good and kind of covers everything that you would need to know. So yeah, as I said before, this is just the same idea that all workers own a replica of the model. Again, I think this is something that's probably easiest seen with a visualization, right? So in the data parallel approach, you have all of this input data that gets split across workers. So for example, GPU 1 might get this one local batch of data that it uniquely processes, and same for GPU 2, 3, etc. One thing worth noting is that in this case, each of the workers retains a complete copy of the model. So as you can see here, each of these different GPUs has the complete model. And so by having the complete model and receiving disjoint subsets of the complete data set, you're able to always be working on, each worker is always working on unique data. And then by implementing a collective communication operation that syncs all of their gradients at each step, allows them to kind of update their weights in an efficient manner. Again, so this is just kind of text that probably isn't terribly worth reading through, but so one thing maybe worth pointing out is that the only operation required to implement data parallelism is this MPI reduce operation, which basically reduces the values from all of your different workers and then broadcasts that reduction back out to all of them so they all have an identical copy at the end of the operation. So there are many different ways of implementing these all reduce operations. And so different libraries might vary slightly in the details of the implementation, but the basic idea being that you need some way to average and sync all of your workers following the gradient evaluation. So here's just kind of another diagram illustrating how the data parallel approach works. So you have some global batch of data that can, be split efficiently across different workers so that each worker is only ever receiving a unique subset of the data. And then the process is more or less identical on each of the different workers. So it has a complete copy of the model that receives its unique subset of the data. After the forward pass of the model, it retains these gradients. The gradients then, following the forward pass and after calculating the gradients, there's this collective communication operation here, which averages the gradients across all of the workers and makes sure that they're all synchronized, that they're all in the same, awaiting the same step, right? They're all at the same point. Once they've all been synced up and have received the average gradients, they can then use these collective average gradients to then update the weights of their local model. And so that's the basic idea and kind of how that process proceeds. So that's kind of it, right, for data parallel. The idea is relatively simple, but it's a pretty powerful idea and it really allows you to, as we saw before, pretty drastically speed up the training process just by kind of introducing more workers and scaling up the general approach, right? So now I'll touch a bit on some of the best practices and general things to keep in mind for when trying these different scaling approaches. So one thing that's definitely worth keeping in mind and always is that computation stalls during communication. And so whenever you have communication operations that need to reduce some values between different workers, that introduces just a break in the computation, right? And so having many communication operations interlaced inside of your computation is generally not preferred. And so finding efficient ways of dealing with how to break up the computation versus communication is important and worth thinking about. So some general best practices taken from, I think these are taken from a slide deck that Corey made a little while ago. But one best practice is to use parallel IO whenever possible. So for example, you could feed each rank from unique files to reduce the kind of shared IO bottleneck from multiple workers. You could use MPI input output to have each rank read. There's the same point. But basically having distributed or well-planned methods for dealing with communications, writing two files, using several ranks to read data and MPI to scatter that data back to remaining ranks is another possible approach. Just again, to kind of reiterate, so it's important to use parallel input output and take advantage of the data storage. Additionally, so on the less-thorough file system, use striping. And using the right optimizations for the machine that you're working on. So these will vary from machine to machine, but should generally be accessible from the documentation page. And if you're not, obviously, if there's ever a case where you're unsure, always ask, and we'll definitely be able to find the right people to be able to help you. Preload data when possible. So that's another general best practice and something to try to use as much as possible. So offloading data to a GPU frees CPU cycles for loading the next batch of data, which can then help to minimize IO latency. To get a kind of broad level overview of how these two different approaches behave and how they differ from one another, it's useful to kind of draw some comparisons between the two. Again, this is probably most easily seen with the picture, right? So just to give some kind of high level context for keeping things straight, maybe, we can look at how the weights of the model versus the data being fed to the model are kind of distributed in each of the two approaches. So for example, in the data parallel approach, each of your worker maintains a complete copy of the model, right? So these blue dots here on the left indicate a copy of the model, right? The weights of the model. And each one of these kind of gray squares is a distinct worker. So you can see each worker retains a complete copy of the model as indicated by this kind of blue square. And each one of these workers has a complete copy of that. And they only receive some unique subset of the complete data set, right? So this data set is indicated by this kind of red, larger square. And you can see that each one of the individual workers only receives some kind of unique subset of that data. And that's in contrast to the model parallel approach, where in this case, each worker receives, a complete copy of the data set as they would need to for, to complete the forward pass of the model. But in this case, they only have some subset of the weights. And so the problem with this approach, obviously, as I mentioned before, is dealing with communication and really having effective tools to deal with that. But this is kind of just, hopefully illustrative to keep, another way of distinguishing between the two approaches and helping to keep things straight in your head. Yeah, so again, it's just text, probably not worth reading through, but it's here in case people want to come back and read through it later. Another reference that is probably useful and has a pretty clear discussion of the differences between these two approaches, as well as new kind of hybrid approaches that try to take advantage of some of the best of both data and model parallel trainings. There's this paper on the switch transformer, which just really kind of has a clear discussion of different approaches and the distinctions between the two. These are just figures which have already been seen before. So now, before going into the more hands-on part, I'll touch a bit on some of the things that you need to know and deal with in order to make everything run smoothly. So the examples provided in this section of the tutorial or the workshop use this package Hydra to manage experiment configuration. So it's pretty straightforward to get installed using the base Conda environment. The instructions explicitly for doing so are here, right? So just to make sure you can get a quick interactive job to install Hydra. So from the Theta GPU service node or the Theta login node, you can just request a quick interactive job, load up the base Conda environment using this module load command, activate the base Conda environment, and then install the required packages. So these will, by default, I think, install into the user directory. So it'll probably be in your home directory, but really they just need to be installed on top of the Conda environment so you can use it with the examples provided. Kind of complete end-to-end shell script that can be used to install everything that's needed and run any of the individual examples is shown here. So this is the path to the base Conda environment. Just a case on whether or not you're using Z shell or bash, because that's kind of been a pain point that I've ran into periodically using Z shell. So you need to be a bit careful in how that's initialized. I'm not sure why there are these extra backticks in here. It looks like that's kind of everywhere. So the examples on the GitHub repo are correct. These are just displaying weird in here for some reason. Then, so once you've activated your base conda environment, make sure that you have the required Hydra packages. Just basically run a pip install on those. Get the count of the number of GPUs. In this case, these will be running on Theta GPUs, so this should return 8. But there's just kind of a programmatic way of getting that same information. Then we can find the total number of workers, so the total number of ranks, by looking at the number of lines in this Cobalt node file. And then we can determine the total number of GPUs just by multiplying those two numbers together, right? So each rank will have 8 GPUs, 2 ranks would then have 16, et cetera, and so on. And we can then run any of the Python scripts using this npi run command, where np is again the number of processes, or the number of GPUs in total, and the host file specified by this Cobalt node file. You need to be careful and make sure that the npi run command forwards the path and your LD library path environment variables to all the workers, which again, these are all, I don't know why these backticks are displaying like this. These should all be correct in the GitHub repo. I think they're just displaying weird in here. So next I will so I'll probably go through this on the GitHub repo because it's maybe a bit clearer and I can go through or pull up the code as needed, but this information again is available in the slides as well. So next I'll talk a bit about actually using or putting these ideas into practice and look at first I'll cover using distributed training with Horovod and look at examples in TensorFlow, and both TensorFlow and PyTorch. And then after that, I'll look, depending on time, run through an example that uses Torch DDP. But the basic idea for using Horovod with either PyTorch or TensorFlow are pretty similar. The basic process for initializing things is the same regardless of if you use PyTorch or TensorFlow, and basically follows this kind of outline of steps here. So first you have to obviously initialize Horovod, pin or assign different GPUs to different ranks, scale the initial learning rate by the number of workers to account for the kind of increased global batch size, distribute gradients and broadcast state. So this is kind of that collective communication operation that we'd seen in that figure before. And that's dealt with internally by wrapping your optimizer with Horovod's distributed optimizer wrapper, basically that handles the internals of all of that for you. And then, the general idea is to make sure that workers always are receiving unique data, and to then take global averages when calculating things like metrics, training loss, accuracy, things like that. And then finally, to make sure that you're only ever saving checkpoints from one of your ranks so that you can prevent these kind of race conditions or prevent all of the workers from trying to write to the same file and causing problems. In a bit more detail, how this works, specifically for TensorFlow, for example. Again, these are just the same steps that I kind of just outlined before, but with the additional code included, so you can kind of see how that works. So again, for initializing Horovod using TensorFlow, this is done pretty straightforwardly just by calling this horovod.init. Once Horovod's initialized, you can then assign each available GPU, and you basically, for each of the available workers, assign that their local rank to that GPU, basically for all of the available GPUs. Next, we scale our initial learning rate, again, by the total number of workers, which just basically accounts for the increased global batch size. Next, we need to be a bit careful how we deal with distributing and broadcasting gradients, the kind of collective all reduce operation we'd seen before. So this is done with Horvath explicitly, or this is done with Horvath and TensorFlow explicitly by wrapping this gradient tape with Horvath's distributed gradient tape. And so again, this is just basically a wrapper around the gradient operations, right? So this gradient tape basically takes a record of all of the gradients encountered in this context manager. And then by wrapping that with this Horvath's distributed gradient tape wrapper, it basically, deals with how to handle all of the communication and things like that. We need to, one other little thing to make sure of is that we need to make sure that everything is initialized consistently at the beginning of training. So this basically ensures that all of our workers start from the same point and that things are consistently initialized. Another important point, and something that is just good to keep in mind generally, is that you want to always make sure that all of your workers are receiving unique data. And so this can be done in, kind of two ways naively. So first, you could just randomly select a mini batch from each worker, where each worker can see the full data set, and you can just randomly select a random mini batch from the full data set. In this case, you have to be careful and ensure that each worker uses a different seed in order to ensure that they receive unique data. But that's one kind of approach. Alternatively, you can manually partition the data ahead of time so that you ensure explicitly that different workers only receive different subsets of the data. And there are different ways of doing this. An example for how this can be done for the MNIST data set in TensorFlow is illustrated here. So basically, you can load your data as normal and then shard it using built-in functionality from TensorFlow. Final kind of point worth mentioning maybe is that when you're calculating metrics or quantities of interest, it's important to take the global average of those quantities across all of your workers. So just, in the off chance where one of your workers is in a bad state, or, just for consistency checks, really, it's always good to make sure that you're looking at global averages of things, and that this quantity doesn't vary too much across different workers and things like that. And then finally, making sure that you only are performing checkpointing from one of the workers. And so most typically it's done from rank 0, but again, it's really just important that only one of them is ever trying to do it. For the sake of time, I probably won't go through the Horvath of PyTorch documentation in such a detailed manner, but the process is more or less the same. You begin by initializing Horvath and then assigning each of the workers to whatever the local rank is. Multiply your learning rate by the number of workers to account for the increased batch size. And so there's a bit of difference maybe in the details of the specific details internally about how you deal with the communication and syncing gradients and things like that. But again, these are all documented here on this repo and as well in the Horvath documentation and things like that. The details for how you deal with the data are again a bit different in PyTorch, but the basic idea is the same. And again, then finally, you know, this making sure that you're doing a global averaging of quantities that you're interested in. And then I guess maybe it's probably worthwhile to see, you know, how this works or how these things look hands-on. So make sure that I have the GitHub repo here. Pull, make sure that nothing has changed recently. And we can just, for example, go through the examples in TensorFlow and PyTorch to give you an example, or, you know, just to see how these things kind of look as you run them. So here I am in the Horvath TensorFlow directory, and we can run. So I'm already actually on an interactive job, and you can see here I'm running on just a single rank with 8 GPUs, and so this example is going to be a bit limited. And for the example, I can only run on 8 GPUs, but the details for running these. We're running these with, you know, any number of workers as possible just by running this included shell script in each of the directories. But since I'm already in an interactive job, I'll show you how this looks. So for example, to run this main.py file here with the 8 GPUs available, we can just run MPI run, the number of processes 8, host file, just to give you an example of how this would work in the case where you might have many different ranks. Hopefully this should work without an issue. No. Okay, so now it seems to be working. So just to give you an example of how this will look as you run it, you can see this is just kind of details about the initialization. Then it should hopefully progress. And so you can see here, yeah, basically that the details are printed out as it trains, only ever printing from rank 0, for example. And so that's kind of the basic idea. You can see at the end here, we achieve a reasonable accuracy, which is to be expected. And then just for completeness, what we can run through the PyTorch example too. So again, this should behave, or hopefully no issues. So you can see it's received information, or is able to pick up on the fact that in this case we're using 8 GPUs. Again, this is just initial information about the initialization, and you can see it kind of trains as you would expect. And so that all works. That's good to see. Next, I will walk through some of the details on using PyTorch's built-in distributed data parallel library for distributed training. And so there's a lot of information here. I'm not going to go through all of it in too much detail, but there's a lot of links and pointers to different resources on external sites and just different things that I've came across that I found personally to be useful. The one kind of maybe thing worth pointing out that distinguishes DDP from Horvath is that DDP actually wraps your entire model and internally does some computations to figure out what tensors need to be all reduced and when. And so this is advantageous in situations where during a sequential backward pass, for example, the earliest tensors to be used going backwards, which would be the latest in the model, may be ready for an all reduce much earlier than the latest tensors, or those which would be first in the model. So that's maybe a bit confusing, but the point being that DDP can try to do some internal optimizations to figure out if there are cases where it can kind of prepare tensors for all reduces earlier and kind of streamline that kind of internal process. And so it allows for the case of being able to all reduce tensors that are no longer needed in the graph while the backwards pass is still computing. Also has some things, some internal tools for fusing multiple operations and creating larger buffers for tensors. So this is turned on by default in DDP, whereas it's an option that needs to be manually turned on in Horovod. So an additional thing is that DDP also can, take advantage of and nickel on NVIDIA GPUs or glue as the communication backend on CPUs. I think this is also true for Horovod as well. So Horovod also works with nickel or glue as the backend, and so there's not much difference in that regards. The details for initializing and getting DDP set up are a bit more involved and require a bit more manual specification. And so you have that also allows for kind of more customization and specifying things explicitly how you may want them. And this can be done, for example, so there are many ways of doing it, but one way of doing this using MPI for pi is shown here. So the basic idea being that you can get the local rank as this from this environment variable, which should be defined by the MPI call. Then you can just generally just use the MPI for pi to get the size, rank, and then set those as environment variables that PyTorch will look for. So PyTorch, for example, will look for the rank and world size environment variables to be defined, which we can get through MPI for pi library. Then we need to get the master address of the host name of the master rank or rank 0, which we then broadcast to all of the workers so that everybody knows what the master address is or the host name of the main process. And then we can just, set those as environment variables as well, which will be, I believe PyTorch will look for, and are just needed to consistently initialize the communication between all the different workers. And so then once all of your environment variables have been set up and all of the information has been broadcast to all of the workers that need it, you can then use this torch to, instantiate or initialize the distributed environment just using this init process group call, using whatever backend is specified. So for example, nickel or glue, with the rank and world size being obtained from there. And so this should get you everything you need to be initialized correctly. And then equally important is making sure that you tear down the environment correctly. And so you can just put in a little helper function that'll consistently tear down the environment and destroy that created process group. So yeah, unlike Horovod init, which uses MPI and does everything under the hood, DDP is more steps and more options, but by having all of these things being done explicitly, it's a bit clearer and maybe a bit easier to see how everything is done. It's just a bit more transparent, maybe. Then once the kind of environment and everything has been set up, the only remaining thing to be done is to wrap your model in this DDP wrapper. And that will then take care of synchronizing weights and reducing gradients before applying updates. And so basically after initializing the environment and wrapping your model with DDP, everything else is pretty much taken care of for you. I'm seeing some questions in the Slack. I will get back to those in a second, hopefully. And so that's really all of the main points I wanted to emphasize about DDP. So some details on the performance. DDP generally scales better than Horovod for PyTorch at large node counts because it could begin an all-reduce operation before the backwards pass is finished. So as I mentioned before, for example, on Summit with 1500 V100s, and one ALCF model had a scaling efficiency of 97% with DDP compared to 60% with Horovod. So I'm guessing I pulled that from somewhere. I should source or cite that. I want to find where that came from, but I believe it. And so that's generally been the experience that we've noticed here, I think, internally, is the improved performance with DDP as compared to Horovod. For this, in the sake of time, I will kind of browse through the rest of this. So just examples of example performance. Here's things in a table. Some references here. I will now work, or hopefully without problems, walk through the DDP example. And see if this works. So you can see it's initializing everything at the moment. And then, right away, we'll get to the start of training. And so you can see, for example, that the accuracy improves across an individual batch, right? And the global, or the batch accuracy increases along an individual batch, and the global accuracy increases, hopefully. Yeah, and that's consistent with the metrics reported here. And so this will run for 10 epochs. One kind of thing maybe that I haven't mentioned throughout these examples that is worth mentioning for anybody who kind of wants to run through these and look at these in a bit more detail. All of the experiment configuration for all of these examples is managed using this library called Hydra. And it's, so I don't know, I personally think it's a pretty cool little tool. I personally use it in my own research a lot. And the idea being that it allows you to specify experiment configurations using a YAML file. So we can look at the configuration specified in this config.yaml file. And it allows you to basically specify things like, the seed, epochs, general, whatever your different arguments that you might want to provide to your experiment may be. And those can then be accessed using, a object, basically just through object access. And the same way that you would, for example, with argument, using the typical argument parser, you can then just pass in this configuration object as this config object. So there's a bit of, the details behind it maybe are a bit involved, but the basic idea being that you can then specify your experiment configurations using a YAML file, which could be accessed then using just dot notation as if it were a namespace for your argument parser, things like that. So for example, pull it up side by side, right? You can see I access here like config.epochs, which is just stored in the config.yaml file as a key value pair. And so this kind of helps to reduce boilerplate, I think, and is just, there are a bunch of additional kind of nice features about it that you can find in more detail on the website if you're interested, but hopefully that should be enough to kind of explain how it works without having to dive too deep into all of the details. And yeah, so I guess that's really all I wanted to present. So there's an additional example on deep speed taken from the SDL workshop. So this is also a self-contained example that has documentation and should work correctly if you are interested in that. But in the sake of time, I guess that's all I really wanted to cover, and it seems like I will have time for, so I can open it up for questions and things now. Looking in the Slack channel, I see, will the distributed training workflow be the same, or any code changes necessary for ALCF AI testbeds? See what else. Okay, yeah, so yeah, that's kind of, yeah, so we did a good job of answering that. We currently usually only do one worker training for AI testbeds. So yeah, that's something that we might look into in the future, but they're all kind of require specific details, and yeah, so it would have to be maybe manually or custom built, but it's possible. It's definitely possible that it might be something we look into in the future. We mainly want to send in ranks. Can we do that? Yeah. Also, all right. It looks like all of these have been answered. Thank you for that. I appreciate it. So have you ever experienced Horvath init causing a free invalid pointer error after program exit? I don't. I've experienced a lot of weird issues and errors with Horvath, and or some mix of Horvath and TensorFlow. I don't know if I've ran across that explicitly. So Hunter, if you have maybe a bit more context, it might be useful. But so maybe I can't say, off the top of my head with certainty or not. And other than that, yeah, I guess that's all I really wanted to cover. So all of these examples are here on the GitHub repo, and for anybody who wants to look at them in more detail, they should be hopefully more or less straightforward to follow. I've tried to make all of the implementations as consistent between frameworks as possible. So for example, the DDP implementation and Horvath TensorFlow implementation, I tried to make as identical as possible. So they all use the MNIST dataset example. They all use identical network architectures. And they all kind of, they should all be as close to identical as possible. There may be, some issues I didn't or might have overlooked, but I think they should be pretty comparable, and so that should help highlight the differences between them. But yeah, I guess if there are any questions or anything else about any